first up is Chuck Kinzel from Liquidwire. Chuck works in manufacturing development at Liquidwire, where he's productizing the deposition and encapsulation of metal gel conductive material on flexible substrates. He's an active member of IPC's e-textile standards committees. Chuck's going to tell us about liquid metal circuitry for novel integration of active components with e-textile assemblies. Take it away, Chuck.
All right, thank you for that introduction here. Like she said, I'm going to share how we use liquid metal circuitry, what we call metal gel, to add functionality into e-textiles. I'll start off with who Liquidwire is, and then some material properties of the metal gel and why we think those are unique for e-textiles. And we'll follow that up with several examples of how we've integrated functional electronics. So Liquidwire was founded in 2016 out of Portland State University. And earlier this year, we received a Series A investment in private equity. This has been really nice because it's been able to allow us to grow during COVID, add staff, and respond to some interesting opportunities. Our key technology is a metal gel conductor. You can see some of the examples to the right here. The metal gel is shown in the upper figures here is the fully formulated. It's before and after deposition. And the lower right figure is an interesting device we fabricated. It's based on an Arduino design, uses an AT-Tiny processor. And we'll talk more about how we do these fabrications in a little bit here. Some of the more interesting things that have happened with us has been we've had a partnership with Panasonic. They have a substrate that we use, and it's been instrumental in creating these flexible printed solutions. And I'll point those out as we go through the presentation. And the other fun activity we've been participating in is called NextFlex. And we had been a vendor to one of the principals there, and just this year we joined as a full member. So next I'm going to talk about what is metal gel. So metal gel is a alloy of gallium, indium, and tin. Sometimes it's called Gallinstan. We modify this gel with an oxide microstructure and some proprietary additives. So gallium, indium, tin, as you can see in the upper left picture there, kind of in the middle, it's very, very liquid. But when we add do our modifications, it becomes more gel-like, kind of like we call it, sometimes describe it as peanut butter. So it makes it easy to work with then. So originally this was conceived as a substitute for mercury in thermometers, so that it takes care of some of the toxicity problems here. Typically we'll print this on a variety of materials, stretchable substrates like TPU, polyolefins, silicone, and of course the Panasonic material I described. So we've been using several application techniques, stencil, done flexographic printing, and the primary process that we use has been when we call stencil in place encapsulation. So I'll go through that in a few more foils here. So one of the interesting characteristics of this is it's always in a liquid state. So it will flow, extend, recover with the substrate that it's patterned on. The metal gel, since it is liquid, does have to be fully encapsulated, and there is no curing process required. So depending on the substrate, the material will remain liquid well below freezing. The exact point is dependent on what it's encapsulated in. As far as an upper temperature, we've tested this as a hypersonic conductor above 700 degrees C, and it continues to conduct well. So one of our first applications was a linear stretch sensor and pressure sensor. So I'm going to switch to showing you some data on how it performs when it's elongated and relaxed. So this graph and data here is from NextFlex, project call 5.2a. And the work there was to characterize several conductive materials and substrates. So we were collaborating with Dr. Pollux at Binghamton University. So if we look in the lower left at the test coupon, this is a structure that was defined by the project call. So the stretch area that we'll be looking at is this space here. It's about 30 millimeters. These black areas here, we've incorporated a non-stretch fabric. We use that in a lot of areas where we want to limit the elongation to protect parts that may not be able to stand as much elongation as the substrate. So Dr. Pollock's team instrumented this using a 4-point probe to monitor the resistance. So in the upper middle here in section A, this is 1,000 cycles of the device being stretched to 30% of its original length at 0.5 millimeter per second. You can notice that the maximum elongation, the resistance is very constant, and then when it's relaxed, it returns to virtually the same resistance. And in view C here, what we see is the very repeatable nature of this. So it kind of helped us feel good about ourselves in the fact that we had an independent lab looking at the data that we had been collecting internally to verify how well the material will respond. So one of the other things that I wanted to share with you is how does this perform in wash testing? Since we're talking about e-textiles, we want to verify the durability of metal gel in a typical wash cycle while it's integrated on a garment. So the test coupon I'm showing here is a TPU-based sensor. It's one of our original test sensor designs. It's encapsulated in a TPU substrate, TPU being a thermoplastic polyurethane. We bond it with a thermal tape to the fabric. The fabric is a very stretch fabric, typical of what you might see in athletic wear. On one end, we put some probe points. It's a polyamide board. The board serves two purposes. It encapsulates the metal gel at the points we want to do the probing, and it gives us a reliable probe point here. So we engaged a third-party test house to do the testing. We had them run this in a top-loading washer, use the powder detergent on a hot wash cycle, and then tumble dry on low heat. And after each wash and dry cycle, we were having them monitor the resistance of the trace that's embedded in the TPU, and very minimal change in the performance of the trace. So that made us feel very comfortable in being able to use this in fabrics and on garments. So now we know a little bit about what is metal gel and how it, I want to show how it can be used in connecting together active circuitry. So this design here is a demonstration of the finest package geometry we've been able to place on the substrate. So this device is about 35 millimeters by 90 millimeters long. And in this case, the circuitry can decode capacitive touch or an inductive sense. The device that's in the middle here will decode that from analog and convert it to digital to send the information out to be processed or used by some other device to take action. So the really interesting thing on this is the QFN16 package. QFN stands for quad flat no lead. It's a package style that's really become very popular as the cell phone industry has pushed to smaller and smaller packages. For example, the pitch that we're looking at here from this pad to this pad is just at a 0.5 millimeter. The other devices that you'll see on here, these 805 passive devices, that's a small package size for capacitors and resistors. It's not the smallest, but it's very convenient for us to use. We're exploring going to further reductions in the size there. As far as the interconnects, these interconnects are typically a 0.5 millimeter. We can go smaller, but it seems to work to get enough density, and we have that as our default in our design for manufacturability rules. So in this case, we have bonded the FFC cable, the flat flexible cable, to the structure here, and it has a standard standard connector on it that you can take the data into some other device. At least for the prototyping is how we used it. So here we're getting pretty high functionality in a compact space that's, can be embedded in the garment. Again, like our wash test structure using thermal tapes. So the next packaging that we've done is, in this case, an EMG measures the signals from muscles. So the image in view 1 is the circuitry similar to what we had before. In this case, we're using a slightly older technology, the SOIC8. The pitch is a little bigger. It's about 2.5 millimeters or 1/10 of an inch. So coming down to figure 2, this is a fully encapsulated version of the product, and showing its flexibility here with twist and stretch and conformability. And in figure 3, it's wrapped around one of our engineer's arms. And in figure 4, we actually bonded it into a compression sleeve so we can reliably place that on a person's arm. So next I'll kind of go into how do we actually make this. So this is an exploded view of the circuit. We kind of consider this an analogy to how printed circuit boards are made. We start with a base layer, it's the bottom side of our product, and we'll laminate on a layer of traces and fill the slots there with metal gel, and we'll have the via layer that will actually provide the ohmic connection to the next layer of traces. And finally, we have an encapsulation layer. If you're familiar with printed circuit board manufacturing, this would be analogous to the solder mask layer. It defines the pads that the components would be mounted to. And it also serves the purpose of encapsulating the metal gel. And this is one of the places where we use the material from our partners at Panasonic. It has properties such that it helps bond the components down since there's no soldering used to attach the components. So I'm going to switch gears now and go to, how have we done this for a product we just are providing for a demonstrator. In this case, it's the controller for a seat heater in an automotive application. And this is the human interface, the section of it. This would be designed that the heater would sit on top of the main cushion area, and this would potentially drape over the edge. In this case, the customer specified the fabrics and the foams we had to use. So we had to bond to those materials. So starting off the interface, we have an on-off button there at 1 and a light to indicate that you've done it. And what we've done with item 3 is we have, with some structures we've create the appearance of a slider to vary the power control. If you look at the right, it kind of shows you the stack up we had. So we start with the substrate, the material we showed you earlier. We have our foams and then the seat fabric, and it's all bonded together to create a nice, easy feel and usable material that could be integrated into a seat. So I'm going to peel away the fabric here, and we can get a look at what does this look like and how we've implemented this. So we're looking from the opposite side of what I showed you on the previous foil here. And what I want to highlight is the interconnections we've been making here between, in this case, some polyamide boards to their traces. So at item 1, this is the structure that actually provides the capacitive touch and gives the user the feel for having a variable slider to manage the power control. The signals are decoded by item 5. It's the NADD logic, which sends the information through an I2C bus to item 6, which is a microcontroller. And that'll process the signals and then illuminate the LEDs, and also it drives a pulse width modulation, basically pulses the power to the seat heater. So next I've got a video, and we'll see how this runs, of this in action. So here we've got the controller board sitting in the middle. We're using a light bulb as a resistive element, and then the FET is off to the right on another material set up to, yep, there we go, on and off. Your finger sliding up the slider and back down, discreetly setting the levels. And it does remember the level. Some fun with them. The software guys had some fun with that one. So when you've got all this control, you got to, how are we going to get the power to actually heat the seat here? So what I've got here is a conductive fabric that was recommended by our European partners, NTT, New Textiles Technologies. If you look at figure 1 on the left, this is a cross-section view of the conductive fabric. It's a spacer mesh material, and woven on the top and the bottom of the faces is a conductive element. It's a stainless steel wire that's in there. It's interesting in the way they did this, that the stainless steel actually is conductive in one direction only, the way they have woven this. So there's minimal crosstalk left to right, and it's also fairly isolated between the top and bottom faces of the fabric. So we've been able to use that successfully to independently power one side or the other. We happen to choose, in this case, to have both sides powered for redundancy. So if we switch over to figure 2, this shows how we're actually getting the metal gel in to create the conductive path. We laminate a couple pieces of TPU material, and in this case, the item 2 is the TPU. It creates a well that we can put the metal gel in, and the metal gel will make the ohmic contact down into the fibers and to the stainless steel. So what we thought was kind of interesting about this is that it's a novel way to put a connection into something that a textile that has conductive fibers and will allow yourself to have a stretch, elongation, or even over some fairly difficult topology and have a reliable contact. So I'd like to leave you with a few thoughts here. You know, I hope this informs you on some new opportunities for, you know, integrating functionality into e-textiles. We really think that this will help with high flexibility and survivability, that it's going to be capable of surviving the wash and dry cycles. And really it's a new opportunity for complex functionality such as decoding analog data and rapidly converting it to digital so that you don't suffer any of the adverse consequences of having analog signals being susceptible to noise or ESD or other contamination, and that this can be integrated really into any textile using common bonding techniques. So I really appreciate your time and look forward to your questions in the Q&A session.